standard level, paper 1, multiple choice. Very easy question to start with. An object falls freely from rest through a vertical distance of 44 meters in a time of 3 seconds. What is the value for acceleration, free fall? Well, it falls freely from rest, so the answer is D, 9.8. No calculation necessary. Number 2 is also a simple question where you have to remember the order of magnitude for the frequency of visible light. This is something you are going to have to learn off by heart. The frequency would be closest to 10 to the 15. This is a piece of information that's much easier if you remember the wavelength rather than the frequency. That range is approximately 400 to 700 nanometers. You can do a simple conversion using the wave equation. Question 3. A woman walks north at 1 meter per second, so that way, before turning through an angle of 90 degrees to travel east without any change in speed. Now this question's not as easy as it looks because the change in velocity, delta v, would be equal to v minus u. Now if we redraw this vector, because this is u and this is v, to represent v minus u, it would look like this, v plus minus u. Now this looks like this. Our velocity, v, is the vector to the east, but this time we're going to add minus the initial vector, so it's going to go down south. So the answer, believe it or not, for the change in velocity, not for the final velocity, but for the change, would be D, root 2 to the southeast. Question 4 is on the high-level video. Question 5 is also on the high-level video. So here's an interesting question. It's a projectile question and a momentum question as well. So we have a simple projectile, no air resistance, and the question's asking, what is the change in momentum? Now initially it might seem like there is no change in momentum, but momentum is mass times velocity. The change in momentum would be mass times velocity at the end minus the initial. So is there a change in velocity? Well, horizontally there's not, because horizontally u and v stay the same because there's no acceleration. Vertically, the initial velocity u, or in this case it's called v, vertical velocity, seems to be the same at the beginning as it does at the end in magnitude, however. But as you can see, its direction's different. The initial velocity, v underscore v, is positive, or if it's positive, then the vertical velocity at the end would be negative. So we do have a difference. So let's substitute that into our values above. We can use minus or plus convention initially. I'm going to start with plus. So our final velocity is minus m mass, vertical velocity, minus the initial, which is v, positive. So this gives us 2mv. So that gives us, it gives you a minus value, but none of these are minuses, so they must have used the opposite sign convention, using this as minus and this as plus. And the answer is B. Number 7, a block of wood is placed on a bench. A variable horizontal force, so F varies, and this variable horizontal force is applied to the block, which is initially at rest. F is initially increased and then adjusted until the block moves at a constant horizontal speed, which describes F as the block moves along the bench. Now this is a bit of an unfair question because it doesn't mention friction. It doesn't say it's a frictionless surface. So you have to assume that it is, in fact, on a there is a force of friction on there. The correct answer is it decreases to a constant value, because that constant value, F, must be equal to friction. However, for the purposes of this particular exam, I've decided unilaterally that C is also correct. Because if you have assumed that there is no friction, then the correct answer would be F, as if the correct answer would be C, because that would mean that force is 0 and acceleration is 0 and velocity is constant. But in fact, it's the same idea, but assuming that friction does in fact exist. Now, we're conditioned in these questions to always look for that information in the question, so it's a bit unfair. So I've given credit to both of those answers. The pound is a unit of mass equivalence 0.454, which is a bit of a strange conversion, and it gives you a bit of a clue to the answer. It's used in a limited number of countries, but is rarely used by scientists. Now, the reason for that is because we have SI units, which are kilograms, or sometimes referred to as metric. And the answer is D. The pound cannot be divided into metric portions, which makes conversions or can lead to inaccuracies in conversions. The answer to A can't be the right one unless we assume that scientists are a bit simple. Scientists cannot be sure that other scientists will be able to work in pounds. That's true, but not necessarily relevant. A pound cannot be defined precisely. Well, that's not true. If you use enough significant figures, you can. And the pound is too large. Well, that's not true either. Okay, so the answer is definitely D. Okay, so question number 9, which is a momentum question. And you have a main rocket and a booster rocket at 2 different masses. The booster rocket disconnects from the main one, leaving one section stationary. What is the final velocity of the main rocket? So this is a momentum question. And as you know, momentum is always conserved. Okay, so let's have a look at the relationships that we have to use. Okay, so the momentum before has to equal the momentum after. The momentum before is the mass of both the rockets together times v, and the momentum after is 0 for the booster rocket, which has ended up with no velocity, plus the rest of the rocket times this velocity x, which we're trying to figure out. So to find x, our final velocity then, x, would be equal to this divided by m, which is d. The answer to question 10 is on the high level paper. Question 11. A balloon develops a tiny hole, and molecules leak into the surrounding air. The temperature is unchanged. The initial volume and pressure of the balloon are V0 and P0. How are the new volume and pressure of the balloon related to the initial value? Okay, the trick to this question is remembering that we're now considering still the balloon. So we're not considering the initial volume of air. So the balloon itself has lost some of the molecules, so therefore its volume has decreased. The pressure, assuming it's a tiny decrease, is considered to be the same, as we still have the same atmospheric conditions pushing in. This is a very tricky question. There's always one or two like this, and I wouldn't worry about it too much. The answer is B. The graph shows a variation with volume V of the pressure P of a mixed mass of an ideal gas. The work done is pressure times change in volume, or if there's a graph question, it's the area under the graph. Okay, so what we have here are two basic shapes. One square, which would give us 0.1 times 10 to the 6. Careful with the axes and the prefixes. So we have 10 to the 6 times 10 to the minus 2 plus this area here, which would be the same as before, but divided by 2. And that would give us an answer of C, 1.5 kilojoules. The diagram shows a single pendulum undergoing simple harmonic motion. Y is the rest position here, so which describes the magnitude of linear acceleration and linear speed. Okay, well, the important things to remember is that whenever you have a pendulum movement or spring oscillation, any simple harmonic motion, at the extremes you always have V equal to 0. Okay, so we have a look at our possible answers. Our linear speed is 0 at x and z. Okay, and actually that's pretty much the only one. So the answer is B. And here we have the definition of gravitational field strength. Okay, so gravitational field strength, G, if we rearrange our F equals mg relationship, will give us force per unit mass. And in fact, that's the definition. It's the force acting per unit mass on a small mass placed at that point. So now to waves. We've got amplitude of a wave at a certain distance from a source is A, amplitude, and the intensity is I. At this position, the amplitude is increased to 4A. So if you remember, the relationship is intensity is proportional to amplitude squared. So whatever you do to the amplitude, you have to square it, and that will give you its intensity relationship. The amplitude has been made 4 times bigger, so if we square that factor, it gives us a value of 16. So the intensity is increased by 16. If we go back to our refractive index relationships, for two materials, N1 and N2, when light refracts, okay, we have a relationship which looks like this. Okay, so the ratios of the refractive index gives us an inverse ratio for the velocities. So therefore, in the second medium, V2, we would have V2 equals N1 over N2 times V1. Okay, which could be A or could be B. So now let's think about the wavelength. Okay, if we use the wave equation, speed, V, equals frequency times wavelength. Okay, so if we substitute these values, this relationship for wavelength into this, so if we now substitute this wave equation into our relationship here for refractive index, we have N1 over N2 equals frequency times lambda for the second wave and frequency times lambda for the first one. Frequency, and this is something you're going to have to remember, does not change as the light ray goes into a different medium. So we can get rid of frequency, and if we rearrange to find our new wavelength, we end up with n1 over n2 times lambda 1, which is A. It's the only option available. So the answer is A. Simple question here, which describes best the ionizing ability and penetrating ability of alpha particles? Well, if you remember, we have alpha, beta, gamma. And alpha, being a helium nucleus, has the greatest ionizing because it has 2 positive charges, but having the greatest mass means that it's the lowest penetration ability compared to the other 2. Okay, so we're looking for ionizing ability high and penetration ability low, which gives us B. Resistance. 2 wires of different diameters are made from the same metal. Right, so same metal means resistivity is the same, so we can forget about that. The wires are connected in series with a cell. Which quantity will be smaller in the thicker wire? Well, if you think about resistance, resistance depends on resistivity, and it increases with length but decreases with cross-sectional area. So let's have a look at this. Which quantity will be smaller in the thicker wire? Well, if you have a thick wire, that means the resistance will be lower. Okay, and if the resistance is lower, then resistance equals current. If the resistance is lower, then the current is going to be higher. So it's not current. The drift velocity of the electrons, well, that one's a bit strange, so let's come back to that one in a minute. Let's have a look at C, the number of free electrons per unit volume. Now, if you make the area bigger, then your unit volume is going to be greater, but the number of free electrons per unit volume is going to stay the same. Okay, so that's going to stay the same. It's a property of the material, and by making the volume bigger, you're not going to increase the number of free electrons per unit volume. So it can't be that one. How about the number of free electrons passing through any cross-section of wire per second? Well, if anything, that is the current, and there's no way that's going to be less because the resistance has decreased. So it looks like the answer's B. But just to make sure, drift velocity, if you remember, is current equals NAVQ. Okay, so drift velocity, V, is equal to the current over the number of particles, the area, and the charge. So we can see that drift velocity is inversely proportional to area. So it makes sense that it would be B. Question 19 is on the high-level paper. Question 20 is also on the high-level paper. An astronaut orbits the Earth in a space capsule. Which statement is correct? So an orbit means that we have circular motion due to a centripetal force acting to the centre of the Earth. So can there be no gravitational forces? Well, the answer is nope, because then you wouldn't be orbiting in a circular path. Do the space capsule and the astronaut have the same acceleration? Well, it's the same force acting on both objects. So, yes, you would have the same acceleration. If we have a look at the other 2 options, could it be C anyway? The space capsule and the astronaut are in equilibrium. Or if they were in equilibrium, then there would be no acceleration. And if you remember, if an object is moving in a circular path, we're having a constant change in velocity. So because we have a constant change in velocity, because of the direction, we must be having acceleration, and that must be because there's a resultant force. So it can't be C. And D, the gravitational force on that space capsule is equal to that on the astronaut. It's the same type of force, but the actual magnitude would be equal to the mass times the field strength. So the forces would be different. Question 23 is on the high-level paper. Questions 25 and 26 are on the high-level paper. Okay, so here we have a blade length of a wind turbine is doubled. By what factor will the maximum power output increase? So if you have a look at the relationship, power equals a half times the area times the density times the velocity cubed. Now if you think of a blade sweeping out a circle, what we mean by that area is pi r squared, and the length of the blade would be the radius. So if we change this formula to represent that, we have a half pi r squared times the density of the air times the volume of speed of the air that's moving through it. So we are going to make the turbine length, the radius, twice as big, which means that we need to square that factor. So the blade is twice as big, but the area is now 4 times greater. So the answer is B. Okay, because here we are squaring the radius increase. Okay, and the last 3 questions are on the high-level paper.